Industrial War. In the first half of the 20th century, mobilized millions of vehicles and thousands of armored fighting machines, turning maintenance from a regimental chore into a strategic variable. States entered the late 1930s with distinct assumptions about how to keep fleets running. Germany, with limited oil and a plan for short campaigns, built organizations to sustain high operational tempo through quick field repairs and rapid recovery. Britain, responsible for expeditionary forces and imperial garrisons, emphasized centralized standards and later created a corps-level repair institution to rationalize disparate practices. The Soviet Union, forced by geography to fight across vast distances and severe climates, sought mass production with rugged designs and simplified field service while accepting early war shortages in trained mechanics and spare parts. The United States, with deep industrial capacity, framed maintenance as a layered system of echelons designed to minimize downtime by pushing quick fixes forward and routing major work to rear depots supplied by large-scale parts pipelines. Interwar experiments shaped these choices. British trials with the Experimental Mechanized Force in 1927 highlighted recovery as a prerequisite to sustained mechanized maneuver. Tanks that could not be towed or repaired quickly became immobile obstacles. German army transport planners built on Reichswehr-era workshops to form wartime Werkstatt Kompanien and Heers- and Standsetzungs units intended to follow Panzer formations, lift disabled vehicles off the battlefield, and execute component swaps under canvas or in rail-fed workshops. Soviet industry prioritized designs like the T-34 with wide tracks and diesel engines to endure poor roads, but the supporting system still depended on mobile repair battalions and plant-level overhauls that were not yet numerous in 1941. In the United States, the Ordnance Department codified a five-echelon scheme: organizational checks by crews, unit maintenance by company and battalion specialists, intermediate repair at division and corps, and heavy rebuild at depot and arsenal level. This doctrine assumed abundant tools, recovery vehicles, and a steady flow of assemblies, gearboxes, final drives, road wheels, packaged for quick replacement. Geopolitical circumstances embedded maintenance in national strategy. Germany planned for rapid operations on continental rail nets whose yards could feed army repair parks. Its calculations assumed short campaigns would outpace attrition. Britain anticipated prolonged commitments in seaborne logistics. Repair had to be standardized so that units rotating across theaters could receive compatible service from base workshops at Alexandria, Tel Aviv, or later in Northwest Europe. The Soviet Union, after the 1939 to 1940 campaigns, faced the prospect of industry uprooting and redeployment east of the Volga. Planners expected to rely on evacuation trains, mobile repair echelons, and later on, rebuilt plants at Chelyabinsk and Nizhny Tagil to keep fleets serviceable. The United States, protected by oceans, expected to project power through shipping. Maintenance therefore hinged on packaging, complete knockdown spares kits, interchangeable components, and recovery vehicles shipped with divisions. Public sentiment and resource politics also mattered. Societies accepted rationing of tires, fuel, and rubber, so that armies could run recovery tractors and transport spares. In Germany, synthetic rubber and fuel programs affected engine wear rates and maintenance intervals, increasing the importance of forward workshops to compensate for lubricants of varying quality. In Britain, parliamentary scrutiny over waste encouraged the salvage and reconditioning of engines and gearboxes, generating a culture of return and repair cycles. In the Soviet Union, the evacuation of factories and the mobilization of civilian mechanics into the Red Army created a new labor pool for military repair units, but shortages of bearings and precision tools in 1941 to 1942 forced triage on damaged vehicles. In the United States, public campaigns for scrap metal collection fed foundries that produced replacement tracks and armor spares. The industrial scale enabled entire depot programs to rebuild worn tanks to near new condition for redeployment. Intelligence estimates before major operations routinely weighed repair capacity. German planners for 1941 expected Panzer divisions to incur non-combat breakdown rates that could remove a significant fraction of runners during long advances. recovery sections with heavy half-tracks like Sd.Kfz. 9 were assigned specifically to pull immobilized tanks to battalion workshops within hours to prevent capture or cannibalization by the enemy. British assessments for desert operations estimated daily march attrition from sand ingestion and suspension wear, forecasting the need for mobile light aid detachments at brigade level and base workshops near railheads. Soviet staff studies before counteroffensives in 1942 to 1943 calculated how many tanks could be restored within 5 to 10 days by Army repair battalions if rail spares arrived on schedule. This shaped decisions on whether to commit a tank corps immediately or to wait for a higher percentage of serviceable vehicles. American theater planners in 1943 to 1944 embedded maintenance metrics, mean miles between failure, average turnaround time, recovery rates, into readiness reports for armored divisions. Shipping tables included specific tonnage for spare power packs and track sets to preserve operational ratios after initial landings. These preconditions converged on a common operational truth. In mechanized warfare, the number of vehicles present at the start line seldom matched the number available 72 hours later. The delta was not only battle damage, but also recoverable failures, clutch burnouts on steep approaches, radiator punctures from small arms fire, final drive teeth sheared by abrupt torque loads. Armies that could retrieve, diagnose, and cycle vehicles back to units within 1 to 3 days preserved combat power. Those that lacked recovery assets, tools, or parts saw formations hollow out, even without decisive engagements. Consequently, recovery routes, workshop siting near rail spurs, and the stocking of high-failure components became measures of strategic preparedness on par with fuel stocks and ammunition expenditure. By the eve of large campaigns, each belligerent had translated these lessons into force structure. German Panzer divisions carried organic workshop companies and recovery platoons intended to clear battlefield lanes quickly and return damaged tanks to service at divisional or corps parks. British formations organized brigade-level light aid detachments and, by 1942, integrated a specialized repair service to unify electrical, mechanical, and ordnance work streams. Soviet armies fielded repair and recovery battalions with cranes, welding trucks, and mobile machine shops, while central depots allocated scarce transmissions and engines according to front priorities. American armored divisions deployed ordnance maintenance battalions with wrecker trucks, tank retrievers, and contact teams equipped to replace a power pack in the field, backed by depots capable of full rebuilds. The stage was set for campaigns where repair cycles, not just firepower and maneuver, would shape outcomes. Formations would win or fail not only by what they destroyed, but by how quickly they turned their own disabled machines back into runners. War began to test these systems the moment mobile operations opened. In September 1939, German field orders for the drive into Poland assigned each Panzer regiment recovery sections with heavy half-tracks, primarily Sd.Kfz, 9 rated at 18 tons, plus Werkstatt Kompanien equipped with welding sets, portable lathes, and spare final drives. The intent was to clear roads within hours, return runners to battalion parks by nightfall, and pass write-offs to corps parks near railheads. Reports from the 19th Army Corps under Hans Guderian noted that non-combat stoppages from clutch and cooling failures appeared within the first 200 kilometers of continuous marches. Recovery elements were directed to leapfrog along designated halts so that stranded vehicles would not block column flow. Polish counterattacks with 7 TP light tanks and anti-tank guns forced hasty repairs to suspensions and radiators hit by small-caliber fire, confirming that even minor damage could immobilize a vehicle until a tow arrived. The campaign in the West in May-June 1940 expanded the scale. German Panzer divisions crossed into the Low Countries and northeastern France with mixed fleets of Panzer I to Panzer IV, most below 25 tons, which allowed 2 Sd.Kfz, 9 or a triple tow of lighter half-tracks, to recover a single immobilized Panzer IV. Army repair parks followed rail nodes at Charleville and later Compiègne to shorten turnaround. A typical divisional routine placed contact teams at brigade bounds with stocks of spark plugs, magnetos, track pins, and road wheels. British and French forces countered with their own recovery chains. The British used Scammell Pioneer heavy recovery tractors to pull Matilda de Ferros and Matilda Sioux infantry tanks off roads struck by air attack or bogging. Light aid detachments embedded at battalion level attempted quick fixes under fire. French base workshops around Lille reported a rising backlog for gearbox work on Hotchkiss and Saumur types once the front collapsed. The rail evacuation pattern broke under the pace of operations, leaving field echelons to triage holes for cannibalization. The opening weeks, therefore, produced a comparative lesson. Formations with pre-planned recovery routes and sufficient heavy tractors preserved a higher percentage of their inventory during rapid thrusts. North Africa in 1940 to 1941 tested maintenance under heat and dust. Italian armored units entered the Western Desert with limited heavy recovery capacity and fewer mobile machine shops at brigade level. Long haul distances from Tripoli to the forward line increased the downtime. During Operation Compass in December 1940, British forces advanced from Mersa Matruh to Bardia and Tobruk, with cruiser and infantry tank brigades supported by RAOC and RASC workshops staged along the coastal road. Sand ingress raised daily air filter servicing and accelerated suspension wear, so brigades enforced march discipline and scheduled nightly inspections to arrest cumulative failures. When the Africa Corps arrived in early 1941, German Panzer Regiment 5 used Sd.Kfz, 9 and captured tractors to retrieve Panzer 3 and Panzer 4 during the advance to the Egyptian frontier. Divisional workshops at Amsus and later at Gazala organized rotating lines for clutches and final drives. The early desert battles showed that a 24 to 72-hour repair cycle could restore a significant fraction of temporarily disabled tanks if spares reached forward dumps, but that any break in fuel or parts flow instantly lengthened turnaround times. The Soviet-German War that began on 22 June 1941 imposed still harsher opening conditions. Soviet Tank Corps and divisions deployed large numbers of BT series and T-26 light tanks with high road speed but vulnerable drivetrains when operated off-road over long distances. Army-level Remonte no Evacuazione Battalioni were tasked to recover and repair, equipped with cranes, Comintern, and Voroshilovets prime movers and mobile workshops. In the first weeks, large encirclements and rail disruption forced many disabled vehicles to be abandoned before recovery assets could reach them. German panzer groups advanced with recovery platoons at regiment and battalion echelons, and corps repair parks moved behind the main supply routes to accept battle damage and component failures. Field notes recorded that a significant share of non-combat losses came from overheating and dust ingestion on long marches in summer conditions. Consequently, both sides increased allocations of filters, radiators, and water pumps to forward stocks. Where railway spurs remained in service, German depots could return damaged tanks to divisions within several days. Where bridges and yards were destroyed, turnarounds stretched beyond a week, and the recovery queue grew. The United States entered large-scale ground operations after landings in North Africa in November 1942, applying a codified echelon system from the outset. Armored divisions landed with ordnance maintenance battalions, tank retrievers based on 6x6 chassis, and contact trucks carrying welding gear and power tools. Units in Tunisia reported early issues with rubber bush tracks and final drives on M3 and early M4 series over rocky terrain. The prescribed practice was to replace assemblies forward at corps level and ship-worn units to depots for rebuild. This required a steady flow of package spares through ports at Algiers and Iran. Allied air supremacy began to reduce road interdiction, shortening the average time between breakdown and tow. American planners also embedded statistical tracking from the opening weeks. Mean miles between failure, average hours to recover, and percentage of returns to unit within 48 hours were recorded in theater readiness reports, tying maintenance performance directly to operational planning. Key command structures emerged clearly during these opening phases. Germany concentrated authority for heavy repair at Corps and Army, with Panzer divisional Werkstatt companies empowered to cannibalize and rebuild under supervision. Britain's early war practice split responsibilities among RAOC, RASC, and unit fitters. By 1942, this would be consolidated. But in the opening period, commanders balanced base workshop capacity against the need to keep light aid detachments forward. The Soviet system combined Army-level recovery battalions with front-level depots that allocated scarce transmissions and engines according to operational priority. This created early bottlenecks when evacuation rail links failed. The United States synchronized division, corps, and depot levels under a single ordnance command chain, which streamlined parts accounting, but demanded reliable port and rail schedules from the first day ashore. Across these theaters, the opening phase demonstrated three operational constants. First, recovery assets had to be close enough to act within hours, or disabled vehicles became obstacles and losses. Second, spare parts flows determined whether divisional workshops could complete assembly swaps quickly, or whether holes accumulated awaiting components. Third, command clarity over cannibalization policy affected force ratios. Permissive rules could restore many runners fast, but reduce the stock of repairable holes for later rebuild. As campaigns moved beyond their first weeks, these initial practices would shape how armies escalated effort, coped with crises, and tried to retain the initiative through controlled repair cycles rather than uncontrolled attrition. Strategic intent translated maintenance from a collection of unit habits into a formal architecture that commanders measured alongside fuel, ammunition, and marching speed. Before major offensives, staff set availability targets and codified the echelons that would achieve them. German KSTN tables prescribed workshop companies and recovery platoons as organic to panzer regiments and divisions, with corps and army parks absorbing battle damage beyond unit capacity. Plans set time brackets, contact teams to arrive within hours, divisional shops to complete component swaps within 1 to 3 days, and corps parks to handle structural repairs on a rolling 5 to 10 day cycle when railheads were close. British organizations, drawing on interwar experiments and mobilization lessons, aimed to standardize practice across theaters. On October 1, 1942, a single service, the Royal Electrical and Mechanical Engineers, unified tasks previously split among corps, creating a clear chain from light aid detachments at battalion level up to Army and base workshops linked to rail and sea terminals. Soviet planning, coordinated by GABTU and front headquarters, defined Army-level repair and evacuation battalions with mobile machine shops, while front depots allocated scarce engines, gearboxes, and track sets according to operational priority. American doctrine framed a five-echelon system, embedding ordnance maintenance battalions and divisions and corps, backed by theater depots and zone of interior arsenals that rebuilt returned assemblies for shipment back to the front. Objectives reflected national strategy. Germany sought to maintain high percentages of runners during fast thrusts. Planners modeled non-combat attrition during long road marches and assigned heavy half-tracks like Sd.Kfz, 9, and later Panzer to clear disabled tanks quickly so columns could keep time-distance schedules. Britain, anticipating extended lines of communication from ports to forward railheads, prioritized standard repair procedures and parts interchangeability, so formations could rotate through workshops without bespoke solutions. Soviet staffs accepted that rapid operational movements would exceed local recovery capacity in the early war. Plans therefore emphasized evacuation of repairable holes by rail-to-rear plants that had been relocated east, while gradually increasing the number of mobile repair units at front and Army level. The United States, facing amphibious entry into contested theaters, built spares into assault loads from the first convoys, packaged assemblies for powertrains and suspensions, mobile welding and machining capability, and dedicated tank retrievers such as M31 and M32 on the M3 and M4 chassis to reduce dependence on ad hoc towing. Supply line design converted intent into flow. German Hilfszeugämter and Feldzeug commands stocked standard component sets for high failure items, final drives, clutches, road wheels, and radiators, moving them forward by rail to core parks pre-positioned near junctions and bridges earmarked in engineer plans. British base ordnance depots at ports received theater allotments and pushed them to advanced ordnance depots connected to rail. Royal Electrical and Mechanical Engineers workshops placed call-forward demands based on controlled returns and inspection data. Soviet front depots, fed by evacuated and newly established plants in the Urals and Siberia, distributed assemblies on the basis of operational directives. Repair trains with cranes and presses were scheduled to cycle between fronts and rear zones to relieve bottlenecks when roads were impassable. American Army Service Forces set theater stockage objectives and days of supply for assemblies as well as consumables. Ordnance depots in North Africa, Italy, and later Northwest Europe used issue and return systems. So, a replace transmission at core level generated an automatic requisition and a backhaul to a rebuild line. Planning documents incorporated explicit recovery tables. March tables identified where heavy tractor sections would stage along routes so immobilized vehicles could be moved off the axis within the hour. Bridge classification data and road priorities ensured that retrievers and transporters, Scammell Pioneer in British service, Diamond T980/981, prime movers in American service, could operate on parallel routes to avoid disrupting combat traffic. Soviet schemes assigned Komintern and Voroshilovets prime movers to Army evacuation detachments, with pre-designated collection points at river crossings and rail sidings. In all systems, the aim was to prevent the conversion of a single breakdown into a roadblock, then to convert a roadblock into a runner through rapid component exchange. Manpower and training were integral. German plans counted on Werkstatt personnel trained to weld armor plates, true torsion bars, and align gear sets in field conditions. Cross-leveling between divisions was authorized before major operations. Britain emphasized standardized trade tests and field expedient manuals so that light aid detachments could execute electrical, instrument, and mechanical tasks uniformly. REME's formation provided a career path that stabilized expertise at brigade and division. Soviet fronts supplemented unit fitters with civilian mechanics mobilized into recover and repair battalions. Training directives stressed rapid diagnostics and the preservation of scarce assemblies by controlled cannibalization. American ordnance units drilled power pack swaps and track work in staging areas before embarkation, while theater maintenance schools retrained personnel on newly issued models to reduce error rates during the first weeks ashore. Metrics tied planning to command decisions. Availability reports tracked the ratio of runners to inventory by type, distinguishing temporary stoppages from battle damage. Recovery rates measured the percentage of disabled vehicles towed within 24 hours. Turnaround times quantified the interval from breakdown to return to unit, disaggregated by echelon. Cannibalization was regulated by policy. German orders permitted it under supervision when parts pipelines lagged. British and American commands required documentation of each component removed to preserve accountability. And Soviet directives balanced rapid restoration with the need to accumulate hulls for plant-level rebuilds. These controls allowed commanders to compare formations objectively and to allocate scarce spares where they would yield the greatest operational effect. Strategic deception and public information intersected with maintenance plans. Announced production goals and re-equipment schedules shaped expectations inside armies and among allies. But staff planning worked from quieter numbers. Predicted failure curves for suspensions on known terrain, attrition of cooling systems in summer campaigns, and the rail capacity required to cycle heavy hulls to rear parks. Weather tables and terrain studies entered repair forecasts. Desert plans doubled air filter issues and scheduled nightly inspections. Forest and steppe plans allocated additional track pins and idlers. Mountain operations integrated engine brake checks to prevent clutch burn on long descents. By the time campaign plans reached final form, maintenance was embedded in the scheme of maneuver. Axis thrust lines designated core parks at rail junctions that engineers were tasked to capture intact. Allied invasion timetables assigned unloading priorities for retrievers and contact trucks to be operational on the first day. Soviet counteroffensive plans sequenced the release of tank corps with the arrival of rail spares at Army depots to raise the share of serviceable vehicles before the main blow. In each case, repair cycles were not adjuncts but prerequisites. The objective was not merely to start with a large force, but to sustain a high percentage of runners at the moment of decision through planned recovery, standardized component exchange, and predictable spare parts flow. The first collisions between ambitious plans and field realities revealed how quickly recovery and repair dictated tempo. In June-July 1941, German panzer groups drove from the Bug and Niemen toward Minsk and Smolensk. Panzergruppe II and Panzergruppe III reported high non-combat stoppages on long approach marches. Divisional Werkstatt companies positioned at pre-marked halts cleared columns by towing overheated Panzer III and Panzer IV to regimental parks. At the Berezina crossings near Borisov on June 29 to 30, 1941, recovery platoons used Sd.Kfz, 9 tractors and bridging ferries, to pull immobilized tanks off ramps so that assault traffic could continue. Soviet Western Front counterthrusts with T-34 and K-VI detachments around Liepel in early July produced a different maintenance picture. Heavy armor absorbed hits but shed tracks and road wheels under sustained movement on damaged roads, forcing Army repair battalions to establish collection points near rail sidings east of Orsha. When rail spurs were cut by air attack or demolition, turnarounds stretched from 2 to 5 days, and the share of runners in some brigades fell despite limited battle damage. Civilians in contested towns encountered blocked streets lined with disabled vehicles. Municipal workshops were requisitioned for welding and machining, bringing local mechanics into military repair chains. In North Africa, Operation Crusader opened on November 18, 1941, with British armored brigades advancing from the Egyptian frontier to relieve Tobruk. Early contacts around Sidi Rezeg showed a clear linkage between quick recovery and sustained pressure. British light aid detachments trailed squadrons and executed track and idler replacements in leaguer areas. Scammel recovery tractors moved Matilda and Crusader casualties to brigade workshops staged on the Tri-Capuzzo. German Panzergruppe Afrika counterattacks on November 23rd to 24th generated sharp exchanges in which both sides reported high temporary losses from mechanical failures aggravated by sand. German divisional parks at Gambud organized rotating lines for clutches and radiators, keeping a portion of Panzer III and Panzer IV available for dawn sorties. Where spares convoys reached forward dumps, units restored dozens of temporarily disabled vehicles within 48 hours. Where fuel or parts columns were diverted by air interdiction, recovery queues lengthened, and brigade commanders curtailed thrusts to avoid creating roadblocks of immobilized armor. On the Eastern Front in late summer 1941, the pocket battles around Uman and Kyiv imposed long road hauls on both recovery and evacuation assets. German Corps, parks near rail junctions at Shepetivka and later at Bryansk, managed steady flows of captured, damaged, and broken down vehicles. The policy of supervised cannibalization allowed workshops to return a percentage of hulls to service by swapping final drives and road wheel assemblies from write-offs. Soviet Southwest Front, short of prime movers, used Komintern and Voroshilovets tractors to tow KV and T-34 hulls to Army collection points. But encirclements often forced the abandonment of vehicles that might have been repairable under different conditions. Civilian rail workers, already mobilized, assisted in re-spiking rails and clearing sidings so that repair trains could move, making rail capacity a practical limiter on repair cycles. Morale effects appeared in unit diaries from all sides. Crews took confidence when retrievers were seen moving quickly, and commanders counted recovery rates as indicators of whether to continue pressing or to pause. Tunisia, in early 1943, offered a first large test of American maintenance under fire. During the actions around Zbeitla and the Kazarine Pass on February 14th to February 22nd, 1943, U.S. armored units fought with M3 and early M4 series against German and Italian formations. Ordnance maintenance battalions deployed tank retrievers and contact trucks along routes from Tebessa toward the passes. Early reports noted repeated track shedding on rocky terrain and transmission issues during rapid redeployments. The prescribed doctrine, assembly replacement forward, rebuild in depots, proved viable where road control allowed two-way movement. The arrival of German mobile groups complicated this by disrupting evacuation routes. American recovery sections adapted by establishing alternate collection points and by prioritizing tools that cleared road axes first, repairing in place only when terrain made towing impractical. As the front stabilized, turnaround times tightened, and the share of runners improved in units that synchronized recovery with traffic control and air cover. The 1942 fighting around Gazala provided an early turning point driven in part by maintenance. In May, Axis forces pushed east with Panzer Armee Africa, while British brigades defended a line anchored on minefields and strongpoints. The formation of the so-called Cauldron after 29th May created a dense zone of fire where recovery teams operated under observation. German engineers cut lanes through mine belts to allow Sd.Kfz, 9 tractors and captured towing vehicles to extract Panzer III and Panzer IV at night. British REME detachments used darkness to pull damaged Grants and Crusaders back to brigade workshops. The side that managed night recovery more effectively entered each morning with a higher proportion of serviceable tanks. Civilians in nearby settlements experienced requisition of water, fuel, and workshop space, illustrating how local resources, welding oxygen, lubricants, machine time, became part of the operational equation. On the Eastern Front in winter, 1941 to 1942, the counteroffensives around Moscow placed different stresses on repair. Low temperatures thickened lubricants and made cold starts difficult. German units adopted heated shelters for engines where possible and increased allocation of antifreeze and fuel for idling during nights. Soviet armies established forward repair points staffed by mobilized civilian mechanics, and used sledges and tractors to move transmissions and engines rather than whole holes when towing was impossible. Where repair echelons kept pace, rifle and tank units sustained pressure, where workshops lagged behind advancing infantry, and the rail net remained disrupted. A growing tail of disabled vehicles reduced available numbers despite local successes. In the Pacific and Burma theaters, first battles with armor were limited but instructive. British and Commonwealth forces in Burma in early 1942 discovered that jungle roads and monsoon conditions restricted heavy recovery movement. Light aid detachments adapted by focusing on small unit tasks, electrical fixes, carburetor work, and track tensioning, while accepting that heavy evacuation would often be delayed until dry seasons or road improvements. Japanese units, operating with lighter tanks and fewer heavy tractors, relied on road control and gradual withdrawal to salvage what could be moved. Immobile hulls were stripped of useful components before demolition. Civilian labor was employed to stabilize embankments and corduroy roads, an example of how non-military inputs influenced whether a disabled vehicle rejoined the line. The Normandy landings in June 1944, though later in the war, demonstrate the same first engagement dynamics on a larger scale. In the first week after June 6th, Allied forces established beach maintenance areas near Bayeux and Courseulles. Ordnance and REME workshops landed early, and tank retrievers came ashore in initial waves to clear exits. German counter-concentrations, including elements of Panzer Lehr and 12 SS, faced air interdiction that complicated daytime recovery. Night became the principal window for both sides to tow, weld, and replace power packs. Civilian garages and machine shops in towns behind the front were assessed for lathes and presses. Requisition capacity expanded the number of component swaps possible per day. Reports from multiple formations tied daily availability to recovery, throughput rather than solely to combat damage, reinforcing the idea that first engagements set the pattern for the entire campaign. Across theaters, the early clashes tested 3 linked variables that commanders could measure. The first was the recovery interval from immobilization to tow. The second was component availability at the first competent echelon. Did a workshop have the right final drive, pump, or road wheel on hand. The third was traffic control, ensuring that retrievers could move without halting combat columns. Where these aligned, formations regained a significant fraction of temporarily lost vehicles within 1 to 3 days and maintained pressure. Where any link failed, blocked roads, missing assemblies, or lack of towing power, frontline strength declined in ways not reflected by production or initial inventories. The opening battles, therefore, turned maintenance plans into observable outcomes. Availability curves bent upward or downward based on how quickly disabled machines were recovered, repaired, and returned to their crews. By late 1942, escalation exposed the fragility of maintenance chains built for short thrusts or limited theaters. In the Caucasus and on the Volga, case blue-stretched German Panzer and motorized formations across rail nets damaged by retreat and demolition. Corps repair parks at Milarovo, Morozovsk, and Kalak worked through queues of Panzer III, Panzer IV, and self-propelled guns with worn final drives after long road hauls. Recovery platoons relied on Sd.Kfz, 9 tractors, and, where bridges were down, ferried holes across with engineer pontoons, doubling tow times. Luftwaffe transport shortages reduced deliveries of precision spares, and rail priorities favored fuel and ammunition over transmissions and radiators. Soviet fronts concentrated repair assets behind counterstroke axes. Army repair battalions set up near Tambov, Saratov, and later east of the Don crossings, handling T-34 and KVI powertrain swaps under canvas with welding trucks and mobile lathes. The crisis at Stalingrad after 19th November 1942 illustrated a systemic divergence. As encirclement tightened, German evacuation of damaged vehicles to rear depots became impossible, while Soviet rail links feeding repair bases east of the Volga remained open. The result was a rising share of serviceable Soviet armor in sectors chosen for exploitation and a falling share on the German side, despite comparable day-to-day combat losses. In Egypt, the Second Battle of El Alamein, from 23 October to 11 November 1942, forced both coalitions to convert planned repair cycles into sustained throughput. 8th Army synchronized light aid detachments, brigade workshops, and newly consolidated Corps and Army workshops under Royal Electrical and Mechanical Engineers' control. Night recovery along the Rahman track and within the minefield corridors brought damaged Valentines, Grants, and Crusaders to forward parks where idlers, track pins, and cooling systems were replaced in prearranged sequences. Axis formations, short of heavy tractors and under persistent air interdiction, staged recovery at Tel el-Akakir and Ruwaysat whenever darkness and dust provided cover. Italian workshops coped with limited stocks of transmissions and magnetos for M13 and M14 series. German units prioritized Panzer III and Panzer IV hulls, cannibalizing less common types. As the battle expanded, the side with uninterrupted spare parts flow and predictable retriever movement re-entered each phase with a higher percentage of runners. Commanders on both sides issued orders restricting daytime towing along main axes to prevent traffic paralysis, a sign that road control had become a maintenance variable rather than merely a movement concern. 1942 to 1943 in the Soviet Union deepened the crisis. Low temperatures increased viscosity and raised cold start failures. Towing power fell on icy gradients. Welding quality deteriorated in unheated shelters. German orders mandated nightly engine runs, allocation of antifreeze, and construction of straw-insulated bays at divisional parks. Soviet directives concentrated repair trains with cranes and presses at railheads, supporting Operation Uranus, and Operation Little Saturn, where to lift turrets and swap power packs within hours mattered as much as ammunition resupply. Civilian workshops in towns like Balashov and Penza were requisitioned for machining crankshafts and gear teeth, tying local industry to front repair echelons. At river lines, both sides adapted by towing subassemblies rather than hulls, an expedient that allowed a small tractor to move a transmission or final drive where a full recovery vehicle could not pass. Tunisia in early 1943 multiplied maintenance demands under air attack and mountainous terrain. From January through March, Axis forces held interior lines that favored short evacuation routes, while Allied forces had to extend roads across wadis and ridges. U.S. Ordnance maintenance battalions near Tebessa and Thala established alternate collection points whenever passes were threatened. British workshops near Mejez el Bab used rail spurs to shuttle heavy assemblies to base workshops. Luftwaffe strikes forced changes in convoy timing and dispersion, which slowed spares delivery but reduced losses of retrievers and contact trucks. The result was a fluctuating availability curve. On days when roads and weather permitted two-way movement, divisional workshops cleared backlogs. During counterstrokes or storms, disabled holes accumulated at roadside laybys, and unit leaders cut march plans to avoid creating bottlenecks that would immobilize entire columns. Escalation also exposed training and manpower gaps. Germany began to feel the cumulative effect of experienced Werkstatt personnel being reassigned or lost. New mechanics required time to qualify on gear alignment and armor welding. Britain accelerated REME trade testing and deployed mobile training teams forward to reduce error rates in electrical and instrument work. The Soviet Union integrated civilian machinists and plant workers into army repair battalions, improving throughput where tools and bearings were available but still constrained by rail capacity and the need to allocate scarce engines to priority fronts. The United States opened theater maintenance schools in North Africa to standardize procedures for M4 series powertrain swaps and turret drive calibration, cutting average job times as formations prepared for operations in Sicily. Political pressures and coalition logistics added layers to the crisis. German leaders prioritized fuel deliveries to mobile groups, which sometimes deferred shipments of bulky spares that could not be produced near the front. British and American staffs balanced production announcements at home with the reality that crating and shipping assemblies consumed significant port and rail capacity. Soviet authorities coordinated front demands with factory schedules in the Urals, using repairable returns to supplement new production. Plant rebuilds of T-34 hulls and engines merged civilian and military maintenance cycles. In all systems, accountability for cannibalization tightened as escalation raised the danger of depleting the pool of repairable hulls. Commanders required documentation of each component removed, and inspectors conducted audits to prevent unrecorded stripping that would undermine long-term rebuild programs. Weather and terrain forced procedural changes. In Rasputitsa, heavy retrievers diverted to corduroy roads and detours, and units pre-positioned skids and rollers to slide holes to firmer ground before tow. In deserts, filters were serviced twice daily. Fuel bowsers supplied idling engines at night to maintain oil circulation and ease morning starts. In mountains, march tables allocated additional tractors for each steep grade and scheduled cooling halts to prevent clutch burn. Across theaters, these adaptations sought to preserve the core metric that defined crisis management, the interval from immobilization to return to unit. Commanders tracked that interval in hours and days, compared it across brigades and divisions, and used it to decide whether to continue a push or to consolidate. Civilian populations experienced escalation through requisition and disruption. Engines, machine tools, and lubricants were drawn from municipal depots. Mechanics and drivers were mobilized for military shops. Rail yards prioritized flat cars for hull evacuation over local freight. In occupied regions, workshops operated under military control, while in home territories, factory repair lines combined with base depots to turn around assemblies for shipment back to the front. Where civilians had access to repair employment, income and ration allocation followed. Where fighting or bombardment cut transport, unemployment and shortages grew alongside military backlogs. By the end of the crisis phase in mid-1943, patterns were visible. Armies that could protect railheads, stage recovery along parallel routes, and stock high failure assemblies at the point of need stabilized availability despite attrition. Forces that extended beyond their recovery radius or lost control of road and rail nodes saw availability decline even when total inventories looked adequate on paper. Escalation had turned maintenance from a staff forecast into a daily determinant of operational freedom. Whether a corps could hold a salient exploit, a breach, or withdraw in order, often hinged on the capacity to tow, swap, and return vehicles faster than the rate at which new failures appeared. By mid-1943, the largest offensives forced maintenance systems to perform at full capacity while under direct pressure. Operation Citadel, launched on July 5, 1943 against the Kursk salient, concentrated armored forces on a scale that exposed every weak link in recovery and repair. German 9th Army and 4th Panzer Army entered battle with several thousand armored vehicles, including Panzer III, Panzer IV, Tiger, and assault guns, supported by Panther prototypes and Sd.Kfz, 9 heavy tractors. Divisional Werkstatt companies were ordered to preposition contact teams at phase lines with stocks of track pins, idlers, final drives, and cooling components. Availability reports in the first days showed rapid divergence between on-paper strength and runners at the line of departure. Long approaches over dust-choked roads increased overheating and air filter clogging. Night recovery to core parks near Orel and Belgorod relied on engineered lane marking to move tractors without jamming assault routes. As Soviet forces counterattacked with tank and anti-tank formations, Army repair battalions behind Voronezh and steppe fronts used mobile cranes and welding trucks to swap T-34 transmissions and road wheels in leaguer zones. Rail spurs at Castornoye and Timovo fed front depots with engines and gearboxes, allowing damaged holes to cycle east, while repaired vehicles rejoined tank corps within 2 to 4 days, where transport remained intact. Civilian depots in relocated industrial towns produced bearings and track shoes that entered the front system by scheduled trains, binding civilian output directly to operational availability. The numbers mattered daily. German Corps recorded that temporary losses from mechanical causes could remove 20 to 30% of a regiment's tanks from morning to evening during peak fighting, with recovery bringing a portion back before the next dawn, if parts and towing capacity were present. Soviet Tank Corps reported similar temporary attrition during counterstrokes, particularly from track shedding and final drive failures under heavy torque. Where Army repair battalions staged within 15 to 25 kilometers of the front and railheads delivered assemblies on time, turnaround for typical drivetrain work held at 24 to 72 hours. Where roads became cratered or rail lines were interdicted, queues accumulated, reducing the share of runners despite steady industrial output. Local civilians experienced the peak indirectly. Workshops commandeered for military use, nighttime noise from welding and engine tests, and priority rail slots for hull evacuation that displaced civilian freight. In the Mediterranean, Operation Husky on July 10, 1943 demanded amphibious maintenance from the first wave. Allied Ordnance and REME units landed retrievers and contact teams with the assault echelons to clear beach exits at Gela, Licata, Pacino, and Syracuse. M31 and M32 tank retrievers began towing within hours to prevent stalled vehicles from blocking causeways. Pre-packed assemblies for M4 series powertrains moved from beach maintenance areas to advanced workshops via Jeep and 2.5-ton truck shuttle. Axis units on Sicily, operating with mixed German and Italian equipment, faced limited heavy recovery and crowded roads that hampered evacuation. Both sides used night towing to avoid air attack. Civil infrastructure became a multiplier. Towns with functioning garages and lathes permitted immediate machining of shafts and bushings. Where ports or bridges were damaged, component flow stalled, and turnaround times grew. As the campaign shifted to Calabria and the mainland in September 1943, mountainous terrain forced retrievers to share narrow roads with combat traffic, and march tables assigned time windows for towing to avoid impasses. Peak operations thus depended on traffic control officers as much as mechanics. In Normandy after June 6, 1944, the bocage imposed unique stresses. Short fields and sunken lanes produced frequent track derailments and suspension damage during hedgerow breaching. Allied forces set up forward repair areas near Bayeux, Saint-Lô, and Caen, with Ordnance and REME workshops arranged in functional lines. Inspection, component swap, test, return to unit. Tank retrievers cleared exits from beachheads and later from bridgeheads over the Seulles and Orne. German formations, including Panzer Lehr Division and 21 Panzer Division, operated under heavy air interdiction that limited daytime movement of recovery columns. Night towing became routine, but shortages of parts, especially final drives for specific models, forced cannibalization under controlled orders. Civilian shops, when intact, were requisitioned for precision work. When destroyed, the loss of local machine tools translated into longer hauls to rear depots. Command decisions about when to rotate battalions through workshops shaped the tempo of major attacks such as Operations Epsom, Charnwood, and Goodwood. Reports show that units with predictable 24 to 48-hour turnaround on common failures could re-enter the line with 70 to 80% of their tanks serviceable for scheduled assaults, whereas units with constrained recovery corridors lagged at 50 to 60%. On the Eastern Front in the summer of 1944 during Operation Bagration, the destruction and capture of rail hubs created a different peak condition. Soviet fronts advanced rapidly, and Army repair battalions leapfrogged along newly seized junctions at Orsha, Borisov, and Minsk. Repair trains equipped with cranes, presses, and generators followed close behind, enabling power pack swaps within range of the advancing spearheads. German units retreating through Belarus faced extended tows and frequent bridge demolitions that delayed evacuation of repairable holes. The ratio of runners to inventory in many German formations fell as disabled vehicles could not be recovered before withdrawals, whereas Soviet units, with rails restored quickly by rail troops and civilians, kept repair cycles shorter. Civilians participated in clearing yards, relaying track, and operating requisitioned machine shops. These actions linked local labor to the speed at which brigades regained fighting strength. In late 1944, during the Ardennes offensive, both coalitions experienced a peak of winter maintenance. German armored units attacked on December 16th with stocks of spares accumulated for the effort. Recovery units moved at night or under fog to tow Panthers and Panzer by fours off icy gradients. American Ordnance battalions established emergency collection points at road nets around St. Vith and Bastogne, routing retrievers on secondary roads to keep the main axes clear for fuel and ammunition. Cold weather procedures increased consumption of antifreeze and lubricants suitable for low temperatures. Units without adequate stocks recorded higher cold start failures and cracked radiators. Civilian garages in the Ardennes towns that escaped destruction contributed lathes and presses to forward workshops, but power outages and roadblocks often limited use. Peak fighting compressed distances between frontline and workshop, increasing the rate at which repaired vehicles re-entered or became casualties again within days. Manpower at the peak became as decisive as materiel. Experienced mechanics reduced job times on critical tasks, such as gear alignment or turret drive calibration by measurable margins. Training deficits showed as repeat failures after improper assembly. Commanders adjusted by concentrating expert teams at the busiest parks, cross-leveling trades between divisions, and sending mobile instruction parties to forward shops. Documentation of cannibalization tightened to preserve the stock of rebuildable hulls for theater depots and home arsenals that were already working at capacity. Across these peak operations, the common pattern was quantifiable: recovery interval from immobilization to tow, availability of the correct assembly at the first competent echelon, and protected movement for retrievers correlated with the percentage of runners committed each day. Where rails and roads supported steady cycling of vehicles and parts, forces could sustain attacks or defense beyond the period originally forecast. Where recovery corridors collapsed or parts pipelines broke, operational pauses or forced withdrawals followed, regardless of initial inventories. Peak intensity, measured by daily sorties or battalion attacks, was therefore inseparable from the invisible work of clearing lanes, lifting holes, and turning failures into returns within a fixed number of hours. Adaptation began at the point of failure and radiated outward through units, depots, and industry. Crews refined routines learned in early campaigns. Daily inspections prioritized systems with the highest failure rates on each terrain: air filters and cooling groups in desert, final drives and torsion bars on broken step roads, electrical harnesses in damp hedgerows, clutch and brake linkages on mountain descents. Squadron leaders scheduled staggered maintenance windows so that a troop's runners were never simultaneously offline. Standard tool rolls expanded to include spare track links, idlers, water pumps, and gasket sets packed in marked crates to reduce search time in darkness. Recovery officers mapped alternate tow corridors and marked culverts, ditches, and weak bridges with load classifications to prevent a tow from failing midway and blocking the axis. Workshop echelons improvised to compress turnaround. Light aid detachments and divisional shops built field jigs to align gear sets and turret racks without factory fixtures. Mobile welders repaired cracked mantlets and road wheel arms with controlled preheat and post-weld cooling using improvised insulation. When railheads were temporarily cut, units moved sub-assemblies rather than hulls. Transmissions, differentials, and final drives loaded on trailers towed by lighter tractors, while cranes and A-frames were fabricated from timber and steel channel to lift components under tree cover. Army and Corps parks standardized layout into functional lines: reception, assessment, component swap, test stand, and return to shorten internal movement and documentation time. Depots recorded job times, identified bottlenecks, and reallocated skilled fitters to the stations with the longest queues. Design adaptation met field practice halfway. Germany introduced purpose-built armored recovery vehicles on existing chassis, including Berge Panther, with winches and spades to anchor during pulls. Orders redistributed scarce heavy tractors to formations with the steepest gradients or worst road nets. Britain expanded REME's remit to include rapid modification programs, such as deep-wading trunking for amphibious approaches and hedgerow cutting devices to reduce track derailments in bokage lanes. Standardized kits allowed brigade workshops to implement changes across battalions within days. The Soviet Union simplified service on later production by rationalizing fasteners and standardizing components across T-34 batches, reducing the variety of parts needed at forward depots. The United States fielded M31 and M32 retrievers on familiar hulls and refined package powertrain assemblies, so corp shops could swap units with fewer adjustments. These measures did not eliminate wear or battle damage, but they shortened the path from fault to fix by removing single-point dependencies. Resource management tightened with experience. Cannibalization policies shifted from ad hoc to controlled programs. Divisions maintained ledgers listing each hull designated as donor, ensuring that vital components were harvested in an order that preserved the maximum number of future rebuilds. Return and repair loops were formalized. A replaced transmission generated a backhaul to depot, a rebuild ticket at an arsenal, and an automatic requisition for a replacement in theater stock. Rail authorities scheduled repair trains, fitted with cranes, presses, and power generation, to circulate between fronts and rear zones, picking up loads of assemblies in one direction and delivering repaired sets on the return. Ports and junctions adopted night unloading cycles for spares to free daylight capacity for fuel and ammunition, reducing mutual interference between supply streams. Countermeasures emerged as the enemy adapted. When adversaries used artillery and air attack to deny recovery corridors at dawn and dusk, recovery units shifted to night towing under blackout, rehearsing hand signals and using reflective markers shielded from observation. Smoke generators were assigned to cover extraction of visible holes in daylight when delay threatened road control. Engineers prepared bypasses around frequent ambush points, so retrievers did not share the same predictable lanes as attack columns. Mine-clearing detachments worked with recovery officers to mark safe pull-off zones inside belts where broken vehicles could wait for night extraction. Defensive forces placed demolitions on abandoned hulls and installed timed incendiaries and lubricants to force the attacker either to commit greater resources to salvage or to accept a write-off. Civilians became part of adaptation networks. Municipal garages contributed lathes, drill presses, and oxyacetylene sets. Railway workshops machined shafts and gears to depot drawings. Factory evacuees staffed temporary machine shops under military control. In agricultural districts, tractor drivers were mobilized to operate prime movers and heavy trailers, increasing towing capacity during Rasputitsa. Local knowledge improved route selection for heavy loads, identifying firm ground, hidden culverts, and seasonal changes in water levels. Authorities balanced these contributions against civilian needs. Requisition of machine tools and mechanics could depress local production, while wages, rations, and fuel allotments to contracted shops created incentives that drew skilled labor back to work after bombardment or evacuation. Innovation also addressed the psychological dimension. Units institutionalized first fix checklists for crews to reduce hesitation after damage, isolate fuel and electrics, inspect track run, test steering clutch, attempt local swap of a road wheel or idler if safe, and signal for tow by prearranged code. Seeing retrievers arrive within hours maintained crew confidence and reduced abandonment of repairable vehicles under fire. Commanders rotated mechanics from exposed forward sites to rear parks to limit fatigue and error rates, and introduced rest cycles linked to job complexity. Theater schools pushed short modular courses forward, training fitters on new models and delivering updated manuals with clear torque values, wiring diagrams, and fault trees that use standardized symbols to overcome language barriers in coalition settings. Equipment footprints evolved to match terrain. In desert commands, water bowsers and air filter stocks were doubled, and test stands were fitted with screens to keep sand ingestion low during engine runs. In forests and bocage, workshops carried timber, rails, and spikes to build temporary hardstands for jacking and alignment. Mountain units received additional winches, snatch blocks, and chain sets rated for specific loads, along with brake lining materials and guidance on engine braking to reduce clutch burn. Winterized toolkits included low-temperature lubricants, antifreeze, battery blankets, and exhaust ducting for improvised engine sheds. Fuel allocations incorporated idling budgets to allow nightly warm-up without trading away march capacity. Doctrine codified these adaptations. Orders defined priorities for recovery based on tactical value, vehicles blocking main supply routes, hulls within enemy observation, and units scheduled for operations received precedence. Standard forms captured each job's failure mode, replaced components, timestamps for tow and return, and mechanic signatures. These data, aggregated at brigade and corps, informed spares forecasts and highlighted systemic faults requiring design change or different maintenance intervals. Commanders began to base operational decisions on measured repair capacity. Pauses were ordered not only for ammunition and fuel, but to allow workshops to reduce backlogs to plan thresholds before resuming attacks. Across all sides, adaptation converged on a measurable objective: keep the interval from immobilization to return within a narrow band despite weather, terrain, and enemy action. Success required synchronized action from crew to factory, from village blacksmith to rail manager, from recovery officer to corps ordnance chief. Improvisation did not replace structure, it filled gaps until structure caught up. Where local ingenuity plugged a break in the chain, an improvised jig, a night tow along a farm track, a civilian lathe turning a critical bushing, formations regained a % or two of runners that compounded over weeks into stronger battalions at the line of departure. Where adaptation lagged, vehicles accumulated in laybys and sidings, and the arithmetic of availability dictated a narrowing choice set for field commanders regardless of courage, intent, or initial stock. Turning points emerged when recovery speed and parts flow altered the balance more quickly than reinforcements could. Around Stalingrad in November 1942, the encirclement that began on 19 November severed German evacuation routes, while Soviet railways east of the Volga remained in service. Army repair battalions of Don and Stalingrad fronts, supported by repair trains staged beyond the river, restored T-34 and K-5 runners in 24 to 72 hours, where rail spares arrived on schedule. Inside the pocket, German workshops faced diminishing stocks of final drives, clutches, and radiators. Towing distances lengthened as perimeter lines contracted. The result was measurable. Outside the pocket, Soviet tank brigades on chosen sectors increased their ratio of runners to inventory week by week, while German formations inside saw the opposite trend even when daily combat losses were comparable. The shift enabled successive counterstrokes on the Chir and Mishkova in early December, where restored Soviet vehicles re-entered action faster than German units could repair or replace. In Egypt a month earlier, the Second Battle of El Alamein, from 23 October to 11 November 1942, showed how standardized maintenance could underpin a decision. 8th Army synchronized light aid detachments, brigade workshops, and corps parks under a single chain to clear minefield corridors by night and return damaged Valentines, Grants, and Crusaders to units for the next phase. Axis recovery, conducted under air interdiction and with fewer heavy tractors, moved at a slower rate. Italian formations reported limited stocks for M13 and M14 transmissions and magnetos, and German units husbanded Sd.Kfz, 9 tractors to extract Panzer III and Panzer IV. As both sides consumed ammunition at planned rates, availability curves diverged because one system cycled common failures, idlers, track pins, cooling components, on a predictable rhythm, and the other could not. The momentum change did not come solely from fire plans. It came from the number of serviceable vehicles present each dawn, a function of the previous night's recovery throughput. At Kursk in July 1943, turning points occurred at brigade scale. In the southern sector on July 12th near Prokhorovka, both coalitions incurred temporary losses from mechanical causes and minor damage that exceeded irrevocable write-offs. German corps expected to return a share of Panzer III, Panzer IV, and assault guns within 1 to 3 days if tow corridors and parts held. Soviet Steppe and Voronezh fronts staged mobile cranes and welding trucks to perform track, road wheel, and transmission swaps within 24 to 48 hours near rail-fed depots. Where lanes stayed open and repair trains reached forward junctions, a tank corps could recover a double-digit percentage of its strength before the next commitment. Where lanes were interdicted or spares failed to arrive, formations fought with the previous day's shortages compounded. Commanders on both sides adjusted operational plans in real time based on availability figures reported each evening, demonstrating that the local turning point hinged on repair cycle length rather than only on ground gained. In Tunisia, in February 1943, the Kasserine period illustrated a reversible turning point driven by route control. Between 14 and 22 February, American armored units initially lost road nets that their ordnance battalions required for two-way towing. As routes via Spitla and the passes reopened under Corps control, tank retrievers and contact trucks re-established collection points and cleared backlogs. Turnaround times contracted from several days to near doctrinal targets for powertrain swaps on M3 and early M4 series. Axis mobile groups, now facing opponents whose runners recovered within 24 to 48 hours, encountered rising resistance from units that had regained vehicles without waiting for replacement shipments. The same forces, with the same nominal inventories, altered the tactical picture by restoring disabled hulls at a new tempo. In Northwest Europe, Operation Cobra on 25 to 31 July 1944 marked a theater-level turning point linked to maintenance density. Allied Ordnance and REME workshops concentrated near St. Lo, organized into lines for inspection, component exchange, test, and return. Tank retrievers cleared sunken lanes in the bocage and later the breakout routes. German divisions, Panzer Lehr, 2 Panzer, and others, operated under persistent air attack that restricted daylight recovery. Night towing mitigated some losses, but shortages of specific final drives and transmissions forced controlled cannibalization that reduced the pool of future rebuilds. As the front opened, Allied formations sustained day-after-day commitments because forward shops held stocks of standardized assemblies for M4 series and could complete swaps within hours. German formations, despite experienced mechanics, saw availability decline when road and rail corridors failed. The turning point thus coincided with a sustained gap between planned and actual return to unit times. On the Eastern Front during Operation Bagration, in June or July 1944, The destruction or capture of key rail hubs produced another maintenance inflection. Soviet fronts restored rails at Orsha, Borisov, and Minsk within days, enabling repair trains to move with the advance. Army repair battalions leapfrogged behind tank and mechanized corps, shortening tow distances and keeping typical drive train work within a 2 to 4 day window. German units, withdrawing across Belarus with bridges down and roads congested, lost the ability to evacuate repairable hulls before demolitions or capture. The ratio of runners fell not only from battle losses, but from stranded vehicles awaiting tow. As rail and road control shifted, so did the maintenance equation, translating directly into the operational collapse of sectors that could no longer regenerate combat power between engagements. In the Ardennes, the offensive that began on December 16, 1944, introduced a winter-specific hinge. German armored formations advanced with accumulated spares and retrievers, moving mostly at night or in fog to avoid air attack. American Ordnance battalions established emergency collection points at Saint-Vith, Bastogne, and along the Meuse approaches, routing retrievers on secondary roads and instituting priority queues. First, hulls blocking main supply routes. Second, vehicles within enemy observation. Third, units tasked for counterattacks. Low temperatures increased cold start failures and cracked radiators where antifreeze stocks were inadequate. As weather cleared, Allied air interdiction constricted German tow corridors, while American recovery regained pace. The turning point unfolded as the side able to restore runners within the planned 24 to 72 hour band accumulated usable strength for counteraction, while the other faced growing lines of immobilized vehicles left at verges and crossroads. Naval and air transport occasionally created or reversed turning points by altering parts flow. In the Mediterranean in late 1943 and early 1944, ports at Naples and later Anzio served as funnels for package assemblies. When unloading and road security met schedule, corps workshops could maintain planned swap rates. When port damage or convoy delays interrupted arrivals, the effect propagated within days to availability at the front. Comparable dynamics applied on the Eastern Front when river crossings lagged bridging plans. A missed ferry cycle for heavy tractors or a delayed train carrying transmissions immediately widened the gap between immobilization and return, with visible consequences in daily readiness reports. Across these cases, the decisive shift was not abstract. It appeared in ledgers, percentage of runners by type at evening report, average hours from immobilization to tow, average days from tow to return, backlog of hulls awaiting a specific component. Turning points corresponded to moments when those numbers crossed thresholds embedded in operational plans. When recovery, repair, and supply stayed within those bounds, commanders retained freedom to attack, hold, or withdraw in order. When the numbers fell outside because corridors closed, parts failed to arrive, or manpower thinned, plans contracted regardless of intentions. The campaign's visible outcomes therefore traced back to an invisible variable measured in hours and days. The time it took to lift a disabled hull, change the failed assembly, and send the vehicle back to its crew. Withdrawal converted maintenance from regeneration to triage. When orders shifted from holding ground to delaying action, recovery officers reprioritized TOWs. First, vehicles blocking main supply routes. Second, hulls within enemy observation. Third, equipment designated for demolition if lift was impossible. Documentation condensed to essential entries, identifying donor hulls, stripped assemblies, and demolition charges laid with timed fuses. Corps parks received authority to destroy stocks that could not be moved before bridges were blown. Railway commands scheduled last trains for power packs and transmissions, then for tools and machine benches. Heavy hulls followed only if flat cars remained. Civilian workshops under military control were returned to local authorities, with inventories of machine tools and lubricants. Where evacuation was infeasible, lathes and presses were disabled to prevent immediate enemy use. In North Africa, the campaign closed with capitulation rather than organized evacuation. On 13 May 1943, Axis forces in Tunisia surrendered. Allied Ordnance and REME teams cataloged captured depots, sorted usable assemblies by type, and scrapped damaged stock that could not be integrated into Allied fleets. The process mirrored battlefield repair, but in reverse. Assemblies moved from forward dumps to centralized yards for inspection, disposal, or reissue to training units. The experience influenced later withdrawal policies by showing that intact depots handed an opponent weeks of repair capacity without fresh shipments. Italy's armistice on the 8th of September, 1943, created a different aftermath. German units moved quickly to seize or destroy Italian depots and recovery assets. Mixed parks now supported German and captured Italian types, increasing parts variety. At the very moment, withdrawal routes through Apennine passes narrowed. Allied forces, advancing from Salerno northward, found depots useful only when equipment matched their inventories. Otherwise, captured hulls were stripped for generic items such as bearings, lubricants, and tools. Civilian mechanics who had supported Italian repair chains were vetted and, where possible, re-employed in Allied base workshops, illustrating how labor could be reabsorbed across a front line once control shifted. In Normandy after August 1944, the aftermath of the Falaise encirclement demonstrated how road control and air interdiction during retreat translated into equipment loss. German rear services attempted night tows of Panthers, Panzer IVs, and assault guns from lanes south of Troon, but demolition of bridges over the Dives and Orne reduced evacuation capacity. Allied Ordnance and REME units established salvage sections behind the advance to clear sunken lanes, recover Allied hulls for repair, and strip enemy vehicles for transportable components. Availability figures in pursuing formations rose as repaired M4s and Cromwells cycled back faster than German units could replace or repair their losses in transit, a material echo of the turning point already passed. On the Eastern Front, withdrawal during Operation Bagration in June-July 1944 and later through East Prussia imposed long tows over congested roads. German recovery units faced orders to disable immobilized hulls with explosive charges when evacuation jeopardized corridor control. Soviet fronts organized trophy brigades to collect enemy vehicles and parts, routing them to repair plants or training grounds. Civilian railway workers restored captured yards at Orsha, Borisov, and Minsk within days, allowing Soviet repair trains to move east-west with the front. The combined effects tightened Soviet repair cycles and widened German turnaround times, a divergence that persisted into the Vistula Oder and Berlin operations in early 1945. In the Ardennes, after January 1945, American and British forces reversed emergency procedures used during the German offensive. Collection points at St. Vith and Bastogne transitioned from crisis towing to systematic rebuild queues. Winterized stocks, antifreeze, low-temperature lubricants, battery blankets were replenished before redeployment. German units, now withdrawing under clear skies, experienced daylight interdiction that broke tow sequences and forced additional demolitions. Civilian garages that had supported both sides at different times reverted to local control, but damaged power grids and fuel shortages limited immediate peacetime use. Surrender and occupation reshaped maintenance networks. On 8 May 1945 in Europe, and after announcements on 15 August 1945 in Asia, with formalities on 2 September, military repair echelons stood down or transferred to demobilization tasks. Allied commands inventoried depots across Germany and occupied territories. Usable tools and fixtures were assigned to reconstruction programs, while specialized jigs and gauges were shipped to arsenals or scrapped. Vehicles deemed economical to rebuild entered depot lines for conversion to training or police roles. Others were sold as surplus or broken for materials. Soviet authorities integrated captured machine tools and stock into industrial plans, while maintaining front-based repair trains during the transition to peacetime redeployments. In the Pacific, where armored warfare had been less dense, captured depots in the Philippines and later in Manchuria offered fewer compatible spares for Allied fleets, but tools, presses, and measuring equipment were absorbed into base workshops. Manpower demobilization required structured handover. Units documented outstanding jobs, parts on order, and cannibalization ledgers before release of mechanics to civilian life. Field schools converted to refresher courses for industrial trades. Many mechanics returned to municipal garages and factories with advanced skills, precision welding, gear alignment, electrical diagnostics, that raised post-war productivity. Governments weighed compensation for requisitioned civilian equipment against the need to rebuild public services. In some towns, municipal workshops that had been military parks resumed tram and bus maintenance with salvage fixtures and measuring gear. Environmental and safety concerns, rarely addressed during campaigns, surfaced in the aftermath. Fuel dumps contaminated ground near former parks. Lubricants and coolants were drained from abandoned hulls before scrapping. Unexploded demolition charges in disabled vehicles required specialized clearance. Salvage organizations established standardized yards with controlled cutting areas, fire watch, and residue collection. These procedures paralleled wartime discipline in reverse. The meticulous tracking once applied to assemblies and job times now governed disposal and reclamation. Operationally, the end of fighting did not eliminate the maintenance problem. It reframed it. Armies occupying large territories needed reliable transport and engineering fleets to clear debris, repair roads, and support repatriation and food distribution. Workshops that had rebuilt combat vehicles now overhauled bulldozers, tractors, and trucks. Spare parts pipelines that had delivered final drives and turret motors redirected to civilian priorities. Railway locomotives, buses, agricultural machinery, often using the same depots and many of the same people. Where withdrawal had been orderly and documentation survived, this transition was measured in weeks. Where depots were destroyed or records lost, months passed before stock control and repair rhythms stabilized. The immediate consequence across all sides was a visible redistribution of capacity. Formations that surrendered transferred intact parks and trained personnel wholesale. Those that withdrew in order preserved core tool sets and a cadre of mechanics who became the nucleus of post-war fleets. Civilians who had labored under military direction resumed work in municipal and industrial roles, carrying forward techniques standardized during the war. The battlefield arithmetic of runners and turnarounds gave way to a reconstruction calculus measured in repaired bridges, reopened rail lines, and the number of vehicles, now mostly unarmored, returned to service to rebuild daily life. The long-term significance of wartime recovery and repair lies in how it reframed military power as a rate problem rather than a stock problem. Post-war doctrines across alliances codified that insight. Western armies retained echelon maintenance but refined it into measurable readiness systems. Daily availability by type, mean time between failure recorded at battalion and brigade, and mandated turnaround goals of hours for crew fixes and days for field-level assembly swaps. The British maintained REME as a unified arm, responsible for light aid up to base workshops, its procedures migrating from North Africa and Northwest Europe into peacetime forces in Germany and worldwide garrisons. The United States preserved a layered ordnance structure in Korea and Europe, later simplifying to field and depot levels while keeping the central principle that quick component exchange forward and rebuild rearward stabilized combat power. The Bundeswehr, created within NATO, adopted standardized recovery and parts accounting compatible with Allied depots, while France, Italy, and smaller states aligned their catalogs and training with multinational exercises that tested recovery lanes as rigorously as fire plans. Design followed doctrine. Tanks and vehicles were engineered for maintainability. Modular power packs, standardized fasteners, accessible final drives, and external fittings for rapid tow and lift. British Centurion and later Chieftain incorporated features for field removal of major units. American M48 and M60 families use power plants and transmissions packaged for swap rather than rebuild in place. Later, the M1 introduced turbine-specific tools but kept the quick-change logic. Soviet T-54, T-55, T-62, and T-72 evolved around engines and gearboxes that front repair battalions could lift with organic cranes, reflecting wartime practice of restoring runners near railheads. Warsaw Pact doctrine emphasized repair and evacuation battalions at army level and repair trains at front level, linking operational tempo to rail restoration and depot cycles. Across blocks, armored recovery vehicles matured from ad hoc tractors to specialized platforms with winches, spades, and cranes designed to anchor and pull within load classifications, turning recovery from a risky improvisation into a standard battle function. Cold War operations validated these choices under varied conditions. In Korea, mountainous terrain and winter temperatures forced repeat application of wartime cold weather procedures, anti-freeze stocks, heated bays, and strict brake and clutch discipline on descents. In Middle Eastern wars, fast-moving armored engagements showed how night recovery and strict cannibalization control could restore significant shares of disabled fleets before the next phase, especially where depots sat close to highways and rail. In Vietnam and later expeditionary campaigns, the center of gravity shifted toward trucks, engineering plant, and rotary wing support. But the logic persisted: remove, replace, backhaul, rebuild, return. Peacekeeping and rapid reaction forces incorporated recovery planning into convoy tables. Air-portable retrievers and modular tool sets allowed maintenance to scale with small deployments. Joint operations pushed standardization further. Common lubricants, interchangeable fittings, and shared diagnostic protocols reduced downtime in multinational task forces. The economic legacy reached beyond armies. Wartime analytics, failure curves, life cycle costing, and condition-based maintenance migrated into civilian industries. Railways, municipal fleets, and factories adopted scheduled inspections and component exchange with documented returns to rebuilders. Port, rail, and highway managers treated recovery as a public safety measure. Clearing accidents quickly to reopen routes used the same logic as clearing disabled armor to prevent roadblocks that paralyzed operations. Technical education absorbed wartime skills. Mechanics trained on precision welding, machining, and electrical diagnostics entered post-war labor markets, raising productivity in automotive, rail, and heavy equipment sectors. Tooling engages from disbanded depots, seeded municipal workshops and vocational schools, embedding standardized practices into peacetime infrastructure. Memory and institutions preserve the human dimension. Veterans associations of ordnance and electrical mechanical arms in multiple countries documented methods that rarely appear in combat narratives. How to jack a hull on soft ground, align a turret rack with improvised jigs, or log a controlled cannibalization so a depot could later rebuild a donor. Museums integrated workshop exhibits alongside combat displays, illustrating that the availability curve behind a famous operation depended on welders, fitters, riggers, and drivers as much as on crews and commanders. Civilian communities that had hosted depots or repair trains retained industrial footprints, sheds, sidings, and power infrastructure that later supported regional development. Historiography debated the weight of repair cycles relative to production and attrition. One view stresses industrial replacement. New tanks and vehicles arriving at ports or railheads determine force growth. Another emphasizes the multiplicative effect of turnaround. If a field system returns a large fraction of disabled equipment within days, operational strength increases even without new deliveries. Archival readiness reports, parts ledgers, and depot logs reveal that both were decisive under different constraints. Where shipping and production were constrained, repair preserved combat power. Where production surged and routes were secure, sustained high availability required both inflow and fast cycles. The comparative record across fronts shows that campaigns turned when recovery lanes, workshop siting, and spares flow met or missed thresholds embedded in plans. Environmental and legal legacies emerged as well. Regulations for handling fuels, lubricants, coolants, and explosive residues at depots originated in ad hoc wartime procedures and matured into peacetime standards. Post-war salvage policies formalized safe disposal and reclamation from hulls and machinery, balancing material recovery with public health. These frameworks descended from battlefield practices of draining, documenting, and cutting under supervision. Habits learned because unregulated dumps polluted, and accidental detonations cost lives. Strategically, the core lesson endured. Operational freedom depends on the rate at which forces turn failures into returns. Staffs continued to plan not only for fire and movement, but for the arithmetic of availability. How many runners would be present at the moment of decision after days of attrition, traffic friction, and weather? That arithmetic linked front lines to factories, village workshops to rail managers, and crew drills to coalition cataloging. It compelled commanders to treat recovery corridors, workshop power, and parts trains with the same seriousness as bridges, fuel points, and ammunition columns. In a century defined by machines, the decisive variable often fit in a ledger column measured in hours and days, the interval from immobilization to tow, from tow to component swap, and from test stand to return to unit. The historical significance of field repairs and turnaround is that they converted industrial capacity into usable combat power at the rate required by operations, and when that rate was achieved or denied, campaigns moved accordingly.